Alright, so let's do our first example of calculating a derivative. So what we're going to do is find the derivative. Okay, so I'm going to get a new function. For this function, f of x is equal to x squared. Okay, so I'm going to get that f prime of x, or f dashed x, which is going to be a new function relative to this x squared. And we're going to use first principles again. Soon you'll see this shortcut and it will be glorious, but for now we're using first principles. Once we get this function, we're going to use it to determine, okay, so we're actually going to do the substitution, the gradient at x equals 1 and x equals -2. We're going to have a look at a graph to kind of confirm that. So the first thing I'm going to do is just copy out my formula. So f dashed x is equal to the limit as h tends to 0. Again, because I want to get these 2 points as close together as possible, so it is at that exact instant of whatever my function is, taking an x plus h minus whatever my function is. So my function is x squared right up here. Okay. So what I'm going to do, in place of the x, I'm going to put x plus h. So I've replaced f of x plus h. Well, what does f do? Well, f squares things. So it's going to square x plus h minus x squared. Okay, so this is always just going to be your original function. Now, if I was to expand this guy, please don't tell me it's x squared plus h squared. Every time you do that, it breaks my heart a little bit. Really important that we're using the expansion pattern. So we've got that a squared, sorry, let's try that again. Okay, so it's, if I've got, a plus b squared, well, that's really a plus b times a plus b. When I expand that out, I get an a squared. I get an ab, but I also get a ba, so that's plus 2ab. And then lastly, I get plus b squared. So this x plus h squared over here, okay, this guy here, well, that's going to use this expansion pattern. So when I expand that, that's going to become x squared plus 2xh plus h squared. Okay, so that's just what this guy expanded, and then I just have that minus x squared chilling at the end. Okay, now I can actually simplify this numerator, because I've got an x squared minus an x squared, so those are actually just going to cancel out. So I'm going to end up with 2xh plus h squared. Okay, now I already know that h can't actually be 0 because it's in the denominator, so because I already have that restriction that h can't be 0, I'm actually just going to go through and say, well, that's going to cancel there, and that's going to cancel there. If you have any other terms, again, basically think about it as you could factorize out the h, so this is really h and then 2x plus h, and you can cancel out that h. Okay, so my next step, I just end up, well, that's just, again, the 2x plus h. So I've gone through and I've reduced the fraction, essentially. Okay, now my final little step is to say, well, what would happen if I sent h to 0? Well, this is a well-behaved function, so if I send h to 0, well, that's just essentially going to send that last little part of it to, it's going to send that last little part of it away. Okay, so this part here, this h, that's going to disappear. So my final step, I send h to 0, and I get my final answer. So the equation that determines the derivative of any particular point is just 2x. So at x equals 1, I plug in 1, and that's going to give me the derivative. At -2, plug in -2, that's going to give me the derivative. So let me just erase all this, and we'll do that. Okay, so let's again have a look at actually doing the substitution. Okay, so I want to plug in when x is equal to 1. So if I start with my original function, okay, well, at x equals 1, my original function for my derivative was 2x. I plug in the 1. That simplifies to just simply 2. Now let's have a look at a graph and kind of confirm that when x is equal to 1, my derivative is actually 2. My gradient at that point is 2. All right, so having a look at this graph here, again, looking over here, this is definitely my standard parabola, x squared. And I've just got some point here where this is the x, and then that's x squared. It's controlled by this slider here, so as I move a, the gradient's going to change. So have a think to yourself, when I move a to the value 1, what should it be? So what should the gradient be at 1? Well, we actually just did that question. At 1, it should most definitely be 2. Because when I plugged 1 into 2x, I get 2. Perfect. And that's exactly what should happen. I've confirmed that with a graph, feeling a little bit better about that first principles. Okay, so now when I plug in -2, well, again, I go back to my derivative function, which is simply 2x, plug in -2, and I should get -4. Again, confirming that with a graph, that when I slide to -2, I get -4. Okay, so we're back at my graph. Let's slide this right over to -2. A little bit too far. At -2, does it get? Perfect. It gets exactly to -4. Okay, so that is confirming graphically what that first principles has told us. So that's our first principles example. Again, that's pretty basic in terms of the expanding and the simplifying we had to do. In the next example video, we're going to have a look at something a little bit more involved.